Welcome to another eddycurrent.com action video. Today I'm going to be talking a little bit about the different types of tubing that you might encounter in a power plant environment. And you'll have to adjust your test frequencies to accommodate each one of these different material types. So what do we got? We got the C-Cure 439 stainless Inconel. Inconel comes in a couple different hybrids. You got 600 thermally treated, 690 thermally treated. 690 thermally treated is what a lot of the steam generator tubing has been replaced with because it doesn't crack. At least it hasn't yet. But maybe give it some time. It'll probably crack. Then you got 316 stainless, 304 stainless, Monel, Zircaloy, titanium, 7030 titanium. Then you got something that's dark. I can't read that one or that one. This is aluminum brass, Admiralty brass. Now, what's interesting is you look at these tubes, look at the titanium over here. Look at how thin that wall is, because titanium's strong, right? That's why they put it on fighter jets. And then in contrast, look at some of these smaller tubes. Look how thick the wall is there. So obviously, if you have thicker tubing, you probably need lower frequencies to penetrate through the tube wall. Now, because I have a lot of different tubing that I deal with, and they've been inspected for years, you know, the test procedures are already set up. But, and this is important, they're legacy procedures. So I don't know how they chose the frequencies, you know. So what I'll do is I'll check them. And I usually use the slide rule because that's a real quick and easy way to check for the F90 frequency. And then once you use a slide rule to calculate F90, you just double it for your prime frequency, which is your highest frequency. F90 is your optimum detection frequency. Then you take half of F90, and that will be one of your mixed component frequencies. So you generally use prime frequency and then your quarter prime frequency to mix out tube support plates. And then you'll take prime, divide that by 10, and that's going to be roughly your lowest test frequency, and that's commonly used to locate the support structures. So when you report an indication, you can report its location relative to different tube support structures, because there's always drawing that goes along with each component. So when you hand the client a report and you find an indication, you're going to reference it from a tube support plate. You know, the lazy way to do it is just call it from the tube end, but, you know, tube end plus 385 inches, you know, that's not ideal. But if you could say tube support plate number 5 plus 1.4 inches, that's a little more specific. And of course, all of the modern data analysis software for large scale tubing inspections, they all have software that automatically landmarks and locates, as long as you input the variables from the drawing. So the actual distances, bend radius, you know, the bend radius of your tubes. And let's see, what else can we talk about these tubes? Depending on the type of tubing, you could have specific types of degradation that is most likely to occur. Yellow metals are famous for having ID pitting. Inconel 600, that has been prone to a lot of cracking over the years. That's why they replaced a lot of the vessels that had 600 thermally treated tubing. They used to also plug 600 thermally treated tubes with I600 plugs, and typically all of those plugs have been removed and replaced with 690 thermally treated plugs. Because back in the old days, when you had thousands and thousands of 600 thermally treated plugs installed in I600 tubing, they would crack. So you'd have to go in there and inspect the plugs the plug rolls with a rotating probe. So what's that look like? Well, I'm going to show you. If you've watched my other videos, you've seen me do a couple on fastener hole scanning. I did one yesterday with the Phasek using a rotary scanner. You know, for the rotary scanners, you just put it in the hole and you watch your Lissajou, and then you can see a big old crack. If I go into one without a crack, actually, this hole has a crack, but it's on the other side of the hole. So if I go to that side, then you see the crack. Now, to do rotating coil examinations in tubing, it's real similar to fastener hole inspections. Now I'm going to go on a different type of tubing, Monel. So my guess is the noise is not going to be horizontal. It's going to be something crazy. That's just an example of how you can use rotating coils to examine tubes, because they're really just like big fastener holes, right? But you can't use this scanner in an installed heat exchanger, especially if it's in a radiological environment, because you'd be soaking up too much dose, so that's not good. So how do you do it? Well, instead of having a cal block with holes in it, you'll have a calibration tube that's loaded with different types of flaws. Now, if you're doing a big inspection and there's multiple types of degradation based on your degradation assessment, and that's a document that says what are the most likely damage mechanisms that you're going to encounter. So what you expect to find and what you could find based on operating experience for other similar types of heat exchangers. So your cal standard is going to have every type of flaw in it that you could potentially find during the test. And how do you know if your test system is adequate to find them? You have a calibration standard using representative types of degradation. You can see them in your cal standard. Then you know that when you go into the actual tubing in your vessel, that you'll be able to calibrate in such a way that if there's degradation in the tubing, you'll find it. So instead of having a probe like this attached to a handheld scanner like this one, your probe would look something more like this. Now this is a straight body probe, and this is called delta head. I think that's what they called it. Anyway, it has 3 different coils on it. It's got a plus point. See that? M plus point. That's a differential arrangement. It gives you a dual polarity signal for volumetric flaws, and it'll give you a one polarity type of signal for preferentially oriented flaws like axials or circs. If you calibrate a particular plus point channel and vector axial flaws to go up, circs will go down, and vice versa. So, and then we got a 115 pancake. That's just a pancake coil like you'd find in pencil probes. So, rotating coil exams are surface exams. Just because you stick this probe up inside the tube, you don't calculate fill factor. Fill factor is only for bobbin coils, which are inside bobbin probes that have the circumferential windings that are non-surface riding. That's when you have to calculate fill factor, 70%, 80%, or whatever. And no, 99% fill factor is not the best fill factor because it's too high. That's always a test question that tricks people up. In theory, 99% is best, but you'll be too close to absolute friction. And if there's the tiniest dent or surface imperfection on the ID of the tube, it could restrict passage of the probe. So typically 85% fill factor is good. But when you have surface riding probes like this, liftoff is what would be your troublesome variable. And it's just going to give you a lot of, horizontal noise. And then you have an 080 80 thousandths pancake coil. That particular coil, it's smaller, so it's going to be better for finding smaller flaws. Have you ever seen a pulsed eddy current probe? They're big, right? To look for corrosion under installation. Very penetrating, but because they're so large, they don't find the small, tiny cracks. If you want to find a tiny crack, use a tiny coil. And with that tiny coil, you're going to drive it at higher test frequencies. So the reason they have this coil in this particular head is if they suspect a flaw is primary side initiated cracking, if you run a small coil at a higher frequency, it will confirm in a different way than it would on the 115 pancake at a lower frequency. So, and as this thing spins at 1500 RPMs or whatever it spins at, you're collecting data from all three coils. And then when you do a terrain plot, you know, the nice cool 3D terrain plot with all the colors like you see with the rotating coils and array probes, the data from each one of these coils can be offset by 20 degrees. So as you're flipping through the different channels, you'll see the flaw shift based on what coil sees it. So to overcome that offset, there is a feature in your software called data slewing. So you just take channel 1, if let's just say it's the plus point coil, and then if the 080 or the 115 pancake is 120 degrees away, which it is on the probe, you can just take and adjust your data so it lines up. And then the third coil, you would slew that 240 degrees. So now when you click through channels 1, 2, and 3 for the 3 different coils, they'll always be in the same spot in your terrain plot. So it makes data analysis much more easy. Now, as you can see, this is a straight body probe. And, you know, this scanner is your motor unit. It spins the probe. Well, there's no motor in this probe head, but there is a connection point. So this actually attaches, what has it got? 1, 2, looks like 7 pins. And as you know, all coils, different manufacturers, they have oftentimes very different probe connectors. So you either have to buy adapters, or if you're like me, you try to make your own adapters, which I've made a lot of, but that term F around and find out, that applies to making probe adapter cables, because you can ruin a lot of plugs, and you can also damage your test instrument, and you can also melt your probes or your coils. So you gotta be very careful when you're trying to make your own adapter cables, but I've made plenty. All right, so this would attach to a motor unit, and the motor unit, let's see here, what do we got? Heat exchanger tubes are long, right? So you've got probe shafts like this that are like 100 feet long. And on the end of that probe shaft, or poly they call it, you'll attach a motor unit, which is about probably a foot long or so. And then you attach the probe head onto that motor unit, and you would control it from your data acquisition station. So you can adjust the rotation speed and also the indexing speed, which is in and out. And then a combination of your rotational speed and your indexing speed, you will arrive at a tube pitch, which is the distance that the probe travels between rotation. And you always want to make sure you get plenty of overlap, so you have to calculate what your scans are going to be like. And you also have to have, like with bobbin coil testing, 30 samples per inch. With rotating coils, you got to have 30 samples per inch in the axial direction, and usually 25 or 30 in the circumferential direction per inch. But keep in mind that when you have the circumference, you got to do what? Pi r squared, pi d, whatever the formula is. It can be more than an inch, you know, so that probe's got a ways to travel to get all the way around the tube. So you have to do some calculations to make sure that your resultant digitized or sampled data is giving you enough data points so you don't miss the tiny flaws. And then let's see, well, what about when you're doing U-tubes like that? You can't insert a straight body probe in a tube like that unless you inspect to get it stuck, because you will get it stuck. So they don't use these. the type of probe that you would use for rotating coil exams in U-bend tubes. See, this is a surface riding single coil rotating probe, but it's got beads on it. Attaches to the motor unit. So this whole thing spins around as it articulates or travels over the U-bend. And then what's one last one I got here? This is actually a combo probe for the U-bends. So it has the single coil. See that little shoe on there? Spring loaded so it can articulate and track over the surface of the ID of the tube. And then down here, about what, 2 feet away, you've got a set of bobbin coils. So in one pass of the probe, you can get the very precise surface riding pancake or plus point coil, and you can also have the normal bobbin coil data. So this is a prime case where on your strip charts, if you put the coil on the left here, if you put that in your left-hand strip chart, and you put the coil from the bobbin in the adjacent strip chart, they're going to be separated by like 2 feet in time on your strip charts. So you can go into the software features and align that data so they're at the same location on your strip charts. Then you just flip back and forth between the bobbin coil and the rotating coil, so you can use that in your data evaluation. All right, that's a little bit about tube testing. Hope you enjoyed the video. Thanks for watching.